Our final project was to do the identification of pneumonia from pediatric x-rays. The goal of this project was to develop a neural network that can diagnose a child with pneumonia based off a chest x-ray. Previous studies have demonstrated considerable inter-observer variability among radiologists in the diagnosis of pediatric pneumonia from x-rays, and this is really important because x-rays are a common way of diagnosing pneumonia. Our data set consists of a labeled data set of approximately 8,500 frontal chest x-ray images, split 50-50 between mnemonic and non-mnemonic x-rays.
For this project, we used two convolutional neural network architectures, ResNet 18 and MobileNet V2. ResNet 18 was selected as a baseline because it's widely used in medical imaging and it provides a strong benchmark for performance. Its residual connections help stabilize training and allows the model to learn deeper representations. MobileNet V2, on the other hand, is a more lightweight model designed for mobile and low-resource environments. For training, we split the dataset into 80% training, 10% validation, and 10% test data to ensure reliable evaluation. We also experimented with several hyperparameters to see how they impacted performance. These included two learning rates, 1e to the -4th and 1e to the -5th, two dropout values, 0.3 and 0.5, batch sizes of 32 and 64, and two optimizers, Atom and SGD with momentum. All models were trained using Google Cloud GPU virtual machines, which allowed us to efficiently run multiple experiments and compare results across configurations. Taking a look at the results for MobileNet V2, we can see how different hyperparameters affected performance. From the test accuracy comparisons, most parameters like learning rate and batch size didn't create large differences. However, two factors did stand out. First, using the SGD optimizer led to a noticeable drop in performance compared to Atom. Second, increasing the dropout rate from 0.3 to 0.5 actually improved performance slightly. If we look at the validation accuracy curves below, this trend becomes clearer. The higher dropout helps reduce overfitting, leading to more stable validation accuracy over time. Overall, MobileNet V2 performed consistently well across most settings, which reinforces its strength as a robust and efficient model, especially for lower resource environments.
Since MobileNet V2 and ResNet perform approximately the same no matter what parameters are varied, it's recommended that MobileNet V2 be used as the default architecture since it's lightweight and can run on a variety of devices. In terms of issues and previous things we tried, for the issues we had lots of issues with Colab stability during training. Colab kept crashing, especially if we weren't using the G4 VMs. The same thing occurred with training time, where training time would be excessive if we weren't using the G4 VMs. In terms of prior architectures that we tried but didn't really include, we tried training a ResNet 50 model, which is a CNN consisting of 50 layers. However, its training times were long and it was extremely computationally heavy for this task. To tackle some of these issues that we were facing, we switched to MobileNet V2 from ResNet 50 because MobileNet V2, like we've established, is a small, lightweight model appropriate for this application, and it was able to run quickly without sacrificing performance. And then here are our references. Thank you.